Speaking of IBM and AMD have made big step in quantum computing by running the error correction algorithms on AMD chips instead of requiring yet more qubits. This allows the fragile quantum calculations to be stabilized using low-cost, widely available, non-supercooled hardware, making practical quantum systems more achievable. The milestone moves IBM closer to its 2029 goal of fault-tolerant quantum computing and shows the potential of combining classical and quantum computers for real-world applications. Tom, is this big news, or is this just more quantum is getting better but isn't really here yet?
I think it's big news for this one particular aspect of it. And I do agree that being able to run the error correction algorithms on what I would consider to be standard computing hardware is a big deal. For those of you who did not watch my Conversations episode about quantum computing, basically what happens is that whenever you're trying to measure those qubits to figure out what the data is locked in there, you have to have enough error correction to screen out the noise that's created because there's a lot of extraneous data that's produced when you're doing this measurement. Normally, that takes a little bit more horsepower to do. As you mentioned, a lot of times it's being run on the same computer that's actually doing the work. And that requires a lot of space, a lot of electricity, a lot of liquid nitrogen. Yeah, really, liquid nitrogen. These things have to be cooled within a few degrees of absolute zero in order to be able to run. So on the one hand, you've got cold fusion, which is we want to be able to run fusion at anything less than the heart of a star. And on the other side, you've got warm quantum computing, which means we want to be able to run it anywhere north of 273 degrees, science degrees below zero. And so the idea is here that if you can start getting more precision in your calculations on cheap hardware, it allows you to take the investments that you're doing to make the quantum computer itself run better. And this is where I've had a little bit of disagreement with some of the news that's come out about quantum computing over the last couple of years, is that some companies like Google are racing to produce a computer that has like the massive amount of qubits available to do these calculations, right? Like you hear about, we've got a computer that can do hundreds of qubits or thousands of qubits. And every time I read one of those articles, I didn't see any mention of error correction. And that's for a good reason. For those of you out there that are audiophiles, what happens if you want to make the music louder, right? You go over to the speakers and you turn the knob all the way up. But what happens when you turn the knob all the way up? You increase the noise of everything in the system, not just that beautiful, Johnny Lee Hooker blues album that you're listening to, but all of the stuff in the background that was captured on the recording as well. That's why we have digital signal processors and all kinds of technologies that allow us to screen out that background noise. We're using it right now on this episode of The Rundown to screen out my daughter coming home and slamming doors and walking around in the background. But in order for that to work on a quantum computer, you have to be able to screen a crap load more data. And that is a quantum unit, is crap load. But what you're going to run into is that it becomes relatively expensive. So I'm glad that AMD was able to make this work. I can't wait to see what more applications come out of this. And if you stay tuned for a closer look, I think you might actually find out that we're not the only ones that are interested in seeing what more can come out of quantum computing.